will be, and weakly resistant sediments, high wave climates and sand beaches are going to be much more prone to erosional effects than beaches with low wave climates, very steep shore, very flat coastlines, and more resistant material. So the morphology of the coast and the near shore is important for what responses we will have. For sand beaches, we calculate the amount of shoreline retreat by this thing called the Bryn Rule, which is a very old rule, 1982. Pierre Bryn, who's one of the godfathers, if you like, of coastal work, come up with this theoretical relationship of how beaches will respond to sea level, where R is the amount of retreat, L is the distance from the shoreline out to where waves stop moving sediment, which is what's called the closure depth. A is the amount of is the rise, the amount of acceleration of sea level rise. H is the height of the dunes, and D is the depth out at that closure point. So dune height, beach slope, sediment size all have effect. So the effects of sea level rise on shoreline movements will be variable around New Zealand. But this is just theory. And we haven't been particularly good at applying, or when we apply this theory from Pierre Bryn to how shorelines have responded to this 1.7mm rise that's globally been going on, we find that it doesn't work particularly well because it doesn't take into account things like sediment transport, longshore supply. All right? But no one else has come up with a better relationship. So this is what tends to get used as a conservative approach to what will happen. So we can see at the top is what will happen to erosional coastlines or equilibrium coastlines, they'll erode. Accretional coastlines can change to erosion. They can change from being accreting to erodive or stable. Gravel coasts is something a little different. Gravel coasts tend to, what happens is the height of the beach in a gravel system responds to the height of the waves, and it tends to push material up rather than take it away. And so what we think with gravel systems is that beach heights will actually go up. There'll be some loss of material from the front to do that, but the rates of retreat will be much less. So the parts of Canterbury that are in gravel are going to have much less erosional change. But as I said, if we're supplying more material down our river systems, this may negate all of this type of thing. And we don't know about those relationships. Then we've got cliffs. Consolidated cliffs, if we had an alluvium cliff, really the amount of change that will happen on that cliff will depend on the size of the beach system in front of it. Can the beach system withstand those changes in sea level? If they can't, then we'll be at quite rapid retreat because they are not particularly well consolidated. Things like basalt cliffs, the Banks Peninsula, won't change a heck of a lot, but we'll get some formation of new platforms at the bottom. Estuarine coasts, obviously if we put an extra metre of, half a metre of water in the next 100 years, the size of our estuarine systems change quite a bit. Locations of our mudflats, our estuarine ecology. Trouble is, we've built around most of those. Is there anywhere that Avon Heathcote estuary can expand to? If we had half a metre more of water level? The answer is no. We built right to the edges of it. So we will lose a lot of ecological habitat from around the sides of those estuaries. Now how damaging that is in terms of the way they operate and flood risk and hazard risk as well, we're not actually totally sure. We know it'll get a lot worse, but we're not quite sure what the components will be in there. Right? So sea level rise is important because it does change our level of risk considerably. Why are we interested in this? Well, nationally we have a pretty extensive coastline. Something like 10,000 kilometres of coast in New Zealand, and if we add in all our inlets we get another 8,000 kilometres over our 350 odd inlets. We have one of the longest coastlines, believe it or not, in the Western world. We won't have a very large landmass, but we have a very long coastline. The majority of our population live on the coast. 70% in total live within what we would consider the coastal environment. And of our major urban centres, only Hamilton, Palmerston North and Hastings are not on the coast. So we are coastal people. And we have a high energy wave environment. We have large areas of open ocean on both sides of us. We're exposed to the high westerly wind belt. We're in the roaring 40s. And we're exposed to subtropical cyclones. So there is high energy drivers out there. And we're geologically young and we're active. Most of our coastal deposits are in the Pleistocene age. So they're laid down in the last 25,000 years. They are unconsolidated rock, and most of them are active. We are not old and stable. So we are highly prone and at risk to coastal hazards, both by the natural physical drivers and by where we locate ourselves. This is a sort of risk map. This is a very old map done in the 1980s. But it gives you an idea of what's moving around the coast, and it hasn't changed particularly. The places where it goes in are erosion, the places where it goes out are accretion. And we see we've got a large number of erosional components, we've got a large number of accretional components. But our coastline is highly unstable. Right? This study found that 25% of our coast is in a state of long-term erosion. 56% of it was static, 21% of it was low and prone to inundation. So if we add those up, we've got possibly around 30 to 40% of our coastline has some degree of risk associated with it. Okay. If we look regionally, if we take out Banks Peninsula, if we looked at Canterbury, 75% of the coast is in long-term erosional state. And the remainder of it suffers from short-term erosion within Canterbury. And we have a lot of low coast in the southern parts in South Canterbury and parts of North Canterbury. Over 1,000 hectares has historically been affected by seawater inundation. So that's around the Waiho, Wainono, Washdyke, Seadown sort of areas, and in northern Pegasus Bay. So we within Canterbury are exposed. This is the erosion map for Canterbury, something I did back in the 80s. Again, hasn't changed a lot. We can see the southern coast of Canterbury, the big erosional jump at Timaru, which is a lot of its human influence, we'll talk about tomorrow. And then we go to the North Canterbury mud coast, all in long-term retreat. This is some of the indication of areas that are affected by inundation. This is the one around the Wainono Lagoon, Waiho Rocks area. And we can see a large area of rural land that gets inundated. And it's been repeatedly inundated. And we've repeatedly tried to prevent that by stop banking, etc., and a wasted asset approach. So Canterbury is prone to hazards. Right? I don't think that's earth-shattering news to anybody. These are just further. This is the one north of Timaru. This is some hazard mapping that we've done. These are storms that we know have affected that coastline, and we're at a map. If you're a small rural landowner, which a lot of these places are, highly productive land in terms of cropping, and you get inundated by saltwater, as I said, you're out of production for about 5 years. Financial ruin has affected a number of these places on a number of occasions. So what do we do about it? How do we manage it? The managing the engineering versus planning. Right? That's sort of the old debate. Hard engineering. The traditional methods. The attitude of the engineer is we can build something to fix it. No matter what the problem is, we pour enough concrete at it, enough rock at it, we'll fix it, it'll go away. Right? Now engineering is good if it is done properly. And don't get it wrong that all engineering, coastal engineering is bad. This is an example here in an estuary of a gabion basket, and it's a very effective engineering works. It provides a good solid barrier. It's low energy because it's inside an estuarine environment, so we don't get a lot of reflection. It doesn't look like a lot of loss from in front of it, and there's good amenity value behind it. So it can work well. It can work badly. This is the Hiwa Spit in the Bay of Plenty. You get the feeling that car bodies aren't particularly effective. Forms of coastal protection works. The house is obviously slipped into the hill, and we can see out here some old protection works, some old railway iron type protection works going out to the spit. Often it is done poorly. Normally it's at reasonably high cost to do well. The idea is that a permanent solution is being put in place so we do it once, so we don't really think about maintenance as an issue when we do engineering works. And usually private schemes done on the cheap, such as this one, using anything that we can get our hands on, are almost certainly doomed to failure. The sorts of types of things that we have, here's another one that didn't go particularly well. This is the Brighton Spit. These drums full of concrete were placed at the end of the Brighton Spit in the 1940s and 50s. And they are still there. They're just all covered over at the moment. Corroding drums sitting down on our beach isn't something that we say increases our amenity value particularly. Other sorts are seawalls and revetments. So this is like a seawall, solid rock seawall, up at the top with the gabion. This is a seawall, a timber seawall. This is in Tasman. You see it looks quite good with part of the dune systems in behind it. There is a reasonable degree of beach ridge in front of it. Less effective, potentially, is a Lewis cap revetment. Revetment is something that goes along the coast or a seawall. They both do the same things going along the coast. A revetment tends to be loose material as opposed to a seawall being concrete or solid material. Clay in the coast, what it tends to do is it provides a solid bund, so we get reflection of energy back off it, as we would from the timber. But what happens with the clays is it breaks down and moves into the beach system and clogs up the pores in the beach system, so that we get less penetration and infiltration of water into the beach, so we get greater runoff, greater backwash of energy coming back off the beach, removes material offshore. We tend to lose material. And this is the common fault with revetments, is they actually increase turbulence in this area. Turbulence removes material, we lose our beach. So we have to decide, are we doing protections to protect our beach, or are we doing protections to protect our land? And most of these things have been done to protect our land to the detriment of our beach. But the beach is the natural buffer, it's the one that nature wants to put there. It is actually the best thing to protect. But what happens with hard engineering is we don't tend to work with nature particularly well. And you've seen this one, this is the St. Clair one. Similar thing, energy comes in, cannot be absorbed on a concrete seawall, gets reflected back, so we lose our beach, but it also gets reflected along, and we get this increased energy attack on the end, and hence this term called end effects. And how we normally deal with end effects is really expensive to carry along seawalls. We tend to dump a whole lot of crap on the end of it, which again reduces our amenity values, recreational values, those sorts of types of things. You know. Okay. Groins and breakwaters are something that instead of going along the shore, they go across the shore. All right, perpendicular. So this is Omaha, Northland, and we can see 3 groin systems trapping sediment. Now the first groin system is the one furthest up the beach, and see it's worked tremendously well. Sediment is coming along this plan-shaped curve as we expect it to be, and it's getting trapped in behind this groin, and it's built the beach up marvellously to one side of it. Great opportunity. But that material then isn't getting past that groin, doesn't have the ability to get past the groin, so what was happening to the end of the spit? The end of the spit's getting eroded. The end of the spit gets eroded, then we get all sorts of effects back up in here. So what do we do? We build another groin. Alright, so we build another groin. It's a little less effective at trapping, because it hasn't got as much material to work with, but the end of it gets even getting further eroded, so we build another groin. So what we tend to do when we build perpendicular defence systems, such as groins, it tends to fix the problem at that point, but move the problem along. And what we often end up with is a groin field, a series of groins, rather than a single groin. So what we thought might have been a solution at one point has ended up costing us a lot more money and having to deal with a lot more issues that were created by a poorly designed system to start with. Stop banks. Whoops, I didn't miss that one. Stop banks are flooding defence systems, a wasted asset approach. So what it is what we say is this land is going to get flooded. We'll build a stop bank, a bund basically to stop it being flooded. The shoreline is still eroding though. When it gets back into the stop bank we have issues with it because they're not actually coastal defence systems, and the land can start to get flooded again, so we tend to build another stop bank. Right, and that sort of thing's happened in South Canterbury repeatedly since around the 50s, so that we just keep giving up land to protect the land behind it to be flooded, from being flooded. Right? Offshore breakwaters have tended to be a more recent example of hard engineering effects, hard engineering solutions, and what it's working on is, let's take away the energy. So if we put a reef in, an offshore reef, we'll break up the energy, therefore it's got less energy to move material on the beach. So the principle is quite simple. And then behind a reef system we normally get the salient building, we normally get a beach built up. Trouble is they're highly expensive to put in, as we've found at the mount where they've done them for surfing. It's very hard to actually design them to do what they're supposed to be doing. The science around it is not perfect. If there's sand building in behind it, that sand is actually coming from somewhere else, so we may have transferred issues. And they only tend to be very short locational effects. So what, for example, one beach where I've been looking at, Rewa is probably 4 or 5k beach. To protect all of it, they need something like 5 offshore breakwaters, and each breakwater at around $1 million to $1.5 million each. Like, highly, highly expensive. But the principle behind them is quite simple and very effective. And what you get is that because of the combined amenity, you get the designers saying, well, we can combine this reef to be an amenity value for surfing, and it can be a protection value. My personal view is I don't think we can couple those two things together, because we're actually looking to do different things with the waves. Like for surfing, we're actually trying to increase the wave to give ourselves a surf ride. For hazard protection, we're actually trying to take the energy out and reduce it completely away. Right, so the design is going to be quite different. I don't think you can actually double up those two things. Then we go to soft engineering, which we'll finish after that. Things like, this is working with nature as opposed to the hard engineering where we just ignore nature and say, look, we can put the material in. Soft engineering is working with nature. Beach renourishment is the most common form. This is Mission Beach in Auckland. You can see what it looked like prior to renourishment. Very degraded, low amenity value. Material leaking off this beach continuously. So its use then as recreational asset is only really low tide. We place material in it, it builds up the beach system, and we get a high tide amenity. That's the most common form of soft engineering, and it's working with nature. It's providing what nature wants to provide, which is a beach system or buffer system. Very common internationally, and becoming increasingly common in New Zealand. Trouble with soft engineering, or beach renourishment in particular, is you have to recognise that this sand will also leave this beach. There's nothing to keep it there, right, unless we start to build some groins at the end and things like that and put artificial headlands in. So you have to always buy in to keep doing it. And what a lot of councils in particular, or ratepayers, don't accept is that ongoing cost. This will cost less initially than building the seawall, but they say, oh, yeah, we'll build the seawall, we build it once and it's got an endless lifetime, which is wrong. We do this, we've got to put in $10,000, $20,000, $100,000 every year, and all it does is disappear off the sea every time. But what have we got? We've got an amenity. So what you find is people that come from, say, the geographical background, the geological background, will look for these types of solutions. Those that come from an engineering background will look for the hard solutions. And what we've got to get better at is marrying the two together, and putting them both in together, and maybe putting some end controls and hard ending controls and artificial headland controls into keeping these things there. Now this has been done. We've done this in a number of places around, and I'll look at some of the examples in Canterbury tomorrow. We've done not with sand, but with gravel. Sand bypassing is a common one overseas, where we've got inlets. And we bypass the sand across the inlet so that it gets from one side to the other, because normally it gets trapped by the inlet and we get erosion on the downrift side. Beach stabilisation is something that we do a lot of in New Zealand, coast care type stuff, where we do control of vegetation control, slope control. We regrade the beaches, we control pedestrian access to try and get them to grow and act naturally without our interference. and it's something that New Zealand is very, very active in terms of coastal protection, and all of that can fall into the protection mechanism. And we'll cut it there and talk about the rest of it tomorrow.